Hello everyone, welcome back to my YouTube channel. Today we'll see fuse deposition modeling type of additive manufacturing technique. So let us first see the components of a basic FDM 3D printer. So as you can see in this image, this red spool is the filament. This is the printer screen from where you can control your print settings. This is a cooling fan. Here is the nozzle from which material is extruded, and above this here we have a liquefying chamber. This is heated, and here this plastic filament is changed into a molten state. This is a card reader slot which you can use to input your CAD files. Here is a USB port which can be used to connect this 3D printer to your laptop or any desktop system. Next is this is the printer bed. Here your 3D part is printed. This bed is also heated using a heater which is situated at the base of this bed. This belt mechanism is for the motion along y-axis. These channels in the vertical bar are for the motion along z-axis. And this particular bar and channel pulley system is for motion along x-axis. This enables the 3D printer to move in all the three directions, enabling us to make 3D objects with ease. Let us look into the working principle of an FDM 3D printer. First, a polymeric filament is fed using a pinch feed roller mechanism. Usually, the diameter that is used for this filament is 1.75 mm. This is more or less standard for all FDM 3D printers. So this filament is supplied and made to pass between two rollers. One of the roller is connected to a stepper motor. Suppose this is connected to a stepper motor. This stepper motor provides motion to this roller and it rotates in clockwise directions. This motion enables another roller to move in anti-clockwise direction, thereby pushing the filament down towards the heating chamber. This heating chamber has resistive heaters. These heaters create high temperatures in this chamber, which causes this particular filament to change from solid state to a viscous molten state. Second part is melting and extrusion of the heated material through the nozzle. Now after this heating chamber is the nozzle. So these rollers provide pressure, and this heating creates another pressure which then forces the material out of this nozzle. Now the bed along the z-axis is moved, or the nozzle can move upward. So we have two options, either the motion of this bed, either this bed can be moved lower down, to enable printing, or this nozzle can be moved upward. Now let us see the commonly used materials in FDM 3D printers. First is polylactic acid or PLA. There are certain set of specifications that are required to be maintained for efficient printing. So for PLA, extruder temperature of 180 degrees Celsius to 230 degrees Celsius is necessary, and a bed temperature of 20 degrees Celsius to 60 degrees Celsius. So here comes the question, why the bed needs to be heated. So bed needs to be heated to avoid any warpages, since the filament or the extruded material is at higher temperature of some 150-200 degrees Celsius, and the bed is at room temperature. So these sharp temperature gradients will create the distortion in the part. Hence, if the bed is heated, these temperature gradients are reduced and the distortions are very minimal or even no distortions. Here we can keep the cooling fan on. Next is ABS. ABS is acrylonitrile butadiene styrene. For this, we need extruder temperatures of 210 to 250 degrees Celsius and a higher bed temperature of 80 degrees Celsius to 110 degrees Celsius to ensure proper adhesion of the part with the printer bed. Here, cooling fan must be off. Next is nylon. Nylon is a flexible material that can be 3D printed. For this, extruder temperatures of 240 degree to 260 degrees Celsius are necessary and bed temperatures of 70 degree to 100 degrees Celsius. Because of higher bed temperatures, cooling fan should be off. Next is PETG. This is polyethylene terephthalate glycol. This requires extruder temperatures of 220 degrees Celsius to 250 degrees Celsius, whereas bed temperatures of 50 degree to 75 degrees Celsius that are comparatively lower. Hence, cooling fan can be kept on. Just to mention, ABS has certain problems and it keeps on sticking to the nozzle, and frequent cleaning of nozzle is required in case of ABS, whereas this problem doesn't occur in case of PLA. Nylon is also very sticky in nature and requires frequent cleaning of nozzle. Let us look at the important process parameters that are there in FDM 3D printing. First and foremost is the layer height or layer thickness. So what is layer height or layer thickness? Suppose you have a cube that you want to 3D print. So the height of the material that you can print in one go is your layer height. Suppose this is your layer height. Now layer height influences the strength of the 3D printed part, and there are certain criteria that need to be maintained. Layer height should always be less than the nozzle diameter. Now, why is it so? Suppose your nozzle diameter is 5 mm. Now, when you lay down a layer, then suppose first layer, then if when it is laid down, because of the diameter of the nozzle being 5 mm, the filament that is extruded also has a diameter of 5 mm. Now, if your layer height is higher than 5 mm, then your nozzle will move a distance. Suppose this is 6 mm. Your nozzle will move a distance of 6 mm in the upward direction and then start to print again. As a result, there is an air gap in between. This is inefficient printing, or this won't print. If your layer height is lower than the nozzle diameter, then your nozzle will move a distance less than the diameter of the nozzle. Hence, it will be suppose here. So, the nozzle will press this initially extruded filament, molten material and flatten the upper surface and then spread over a layer of material. This will ensure a surface contact between consecutive layers of the material, thereby ensuring good bonding. Next is nozzle diameter. Nozzle diameter actually affects the part accuracy. Higher the diameter, lower is the part accuracy, and lower the diameter, higher is the accuracy. Next is melting temperature of the extruder. Melting temperature of the extruder actually affects the viscosity of the molten material. This in turn This in turn affects the flow properties and ultimately the surface finish of the printed part. Now comes infill density. Infill density affects the strength of the 3D printed part. Infill density you can define as the amount of volume that is being filled by a material. So, infill density can be varied from 1% to 100%, that is a fully dense material. Higher the density, higher is the strength. Next comes infill patterns. There are multiple infill patterns that are available in the slicing softwares that we use to create the G codes of the parts. So one is lines. There the part is simply made of lines. Suppose this is your part and it will simply be made of lines like this. Next is cubes. where your part, suppose this is the part, and it will be made of cubes like this. This gives like cubes or squares. Next comes honeycombs. So here you can have structures like this, suppose this. Next comes triangles. So here you can have structures like this. You can have triangles going all along. And there are multiple varieties. So these infill patterns, what they does is they distribute the load in different directions. As per the orientation of the material. Hence, we get different strength characteristics depending on the different infill patterns. There are many more patterns available. Next is air gap. The gap between two consecutive lines is termed as the air gap. Next is the raster angle. This is angle of the printed or deposited material with the x-axis. So here, suppose this is the printed material and this horizontal one is the x-axis. So this particular angle is the raster angle. This also plays a role in strength. As one of the studies done by me has found that when this is at 60° or 30°, it has higher strength. Next is raster width. Raster width is the width, this width of the printed material. Width of the printed material. This depends directly on the diameter of the nozzle. So these were the important parameters that are to be considered during FDM 3D printing. I hope FDM 3D printing basics are clear to everyone. Thank you.